So, good morning. It's a pleasure to see you all here. I hope you are going to enjoy very much the school, and I actually was invited to give here lectures. So the title might be a bit misleading because it says Theory on Neutrinos double beta decay. This Neutrinos double beta decay will only cover part of my lectures. The rest will be just an introduction to neutrinos, just that we are on the same page regarding neutrinos, and I will actually assume that you all are familiar with the standard model of particle physics. And from there, we will all, let's say, start our journey and see what neutrinos can offer to us, respecting their properties, and we will come to the neutrinos that can be Dirac or Majorana particles, where the question of that the Majorana is central to neutrinos double beta decay. We will look into different types of how to generate neutrino masses, because that also might be very relevant for what we expect for neutrinos double beta decay. And in the end, we will really discuss this process, and we will see what kind of predictions we can expect from different types of generation mechanisms for neutrino masses, or even other physics. Okay, so whenever you have a question, please interrupt me. If you have problems with, so you will see most of my lectures will be actually on the blackboard. I decided to do that just not to be super fast and then get you all behind. I will show a few slides, just some nice pictures, or up to you whether you find my pictures nice. And otherwise, yeah, if you have problems in reading my handwriting, also please tell me. So, and if you have otherwise questions, see, always please raise your hand, raise your voice, and we can discuss. I'm happy to discuss. There will be Joao who will give the tutorials about these lectures, has prepared some, has prepared several exercises for you and also discussions, so just to get a bit more into the topic yourself. What are we going to start with? We start with something basic. We start with what you know from the standard model. So what the standard model of particle physics tells you, you have a gauge group SU3 cross SU2 left, cross U1 hypercharge. And where do we find neutrinos? We do find neutrinos inside the standard model if we look at the so-called left-handed lepton doublets, which we would write LE1 to be UEL, EL, L2 to be the one with the muon left, and LL3 to be the one with the tau. So all these under the standard model gauge group transform as what one would say is a 1, a 2, and a -1/2. So they don't know about color. They are doublets under SU2 left because we write them in this two column, in this format of a column with two entries, and they have hypercharge -1/2. So the first thing, I want to start very basic and also maybe a few things are just reminding you. So first thing is we find them in three places. We find them here, here, and here. So the first question would be, why are we convinced that there are actually three of them around? So there I would like to remind you of what we see. This is the standard. This is the standard model. We were saying here are the friends which we know. You see there is a hole which we are going to discuss in a minute. And if we want to address first the question, why are we sure that there are three of them, that they actually sit here, let me remind you what we know about the number of neutrinos. So what are the number of neutrino generations? So there we have data from the decay of the Z boson. And actually, as you know very well, at least the experimentalists know very well, it's extremely hard to detect neutrinos. So if we ask about the decay of the Z boson to neutrino, antineutrino, we are actually asking about the invisible decay width of the Z boson. And you see here this fantastic, by now historic plot from lab that was giving you here the center of mass energy, and this is the cross section, and you see the Z boson peak. And you see what's the difference between fitting this peak when you assume that there are 2 light neutrinos, 3 or 4. So what do I mean with light neutrinos here? I mean the ones that are lighter than half of the Z boson mass, because otherwise you would not have this decay channel, and obviously they should couple to the Z boson, and here it's assumed that they couple exactly like what we would predict from the standard model. So you see, there is a perfect fit, so to say, to the fact that there are 3 of them, which makes believe us that there are 3. There's actually information from a totally different world, if you wish. There's also information from cosmology, because neutrinos are very light on all scales that we will learn a bit more also here in this course. And still being so light and weakly interacting, they can have a huge impact on cosmology. They can have a huge impact on what is called cosmic microwave background. So this has been studied very much in detail by the Planck collaboration, and this is results published in 2018. And also on large-scale structure, baryonic acoustic oscillations. And indeed, what you count here is actually not the number of neutrinos, it's the number of all very light species. From the standard model, you would expect that there are 3, because we have 3 light neutrinos. And actually the number which is measured is really extremely close to 3. So this is yet another confirmation that there seem to be these 3 ones that are very light, and apparently also nothing else. So just to say, so this is telling us about really the number, so that we can happily go on with this number 3. The next thing, what you come across, and what everyone tells you, what I already wrote down, that these are left-handed lepton doublets. So which means the neutrinos are left-handed. So what does it mean to be left-handed? So to be left-handed means for a particle at least that left-handed neutrinos, they are negative chirality states. So this means if you apply gamma 5 to a left-handed neutrino, you will get it as eigenstate with a minus. Yeah? And just in parentheses, if you think about the right-handed antineutrinos, these are positive chirality states. So then, apart from chirality, what we also know and what we usually like to introduce is the concept of helicity. So now if you introduce the concept of helicity, this means you introduce the operator H, which is just sigma dot P, which means sigma are is the spin, so you think about the Pauli matrices, and P is the momentum of the particle. So which means actually when we do this scalar product, the helicity is the projection of the spin on the momentum direction. So you would say, indeed you can normalize this also. So that would mean that this is the projection of the spin on the momentum direction, which is P hat. So now the question is, this is an operator you can introduce. You can study its eigenstates and its eigenvalues. So you will find that the eigenvalues are plus minus 1/2 in the standard convention. And the question now, how is this helicity related to what we use in order to describe left-handed and right-handedness? So this is chirality. And now we come to another very fundamental property of neutrinos. It's not only the number, it's also the mass. And as you probably know or have heard already, at least, so if we are dealing with massless particles, chirality and helicity are the same. So, which means if we are dealing with, in our case, massless neutrinos, we know that negative chirality states correspond to negative helicity states. So, which means these two have as eigenvalue minus 1/2. So, what happens if a particle is massive, and this is also true for neutrinos, obviously. If it's massive, this is no longer true that these are identical because you can change your frame, and then you would find that a negative chirality state has a small component of positive helicity. So now you ask how small this is, you can do your computation and you find out that this goes proportional to the mass divided by the energy of the particle. So yet we wouldn't be here if neutrinos were completely massless, so we are definitely in this situation. The next question is, are we in a situation where this has a considerable effect? It would turn out, no, it's not going to have a considerable effect. If you think about this a potential way to measure the mass of the neutrinos, you would find out, no, this is not usually because the mass of the neutrinos, as we will see in a second, is believed to be less than 1 electron volt, while energies, which we encounter in different neutrino experiments, if you think about reactor experiments, accelerator one, solar neutrinos, or also ones coming from the atmosphere, even outside our galaxy, they will have masses which are very often, they will have energies which are very often in the MeV GeV. So this is not a way to measure this mass, but this we have to keep in mind that there's a difference between the chirality and helicity. And however, this brings us to the point that now these are going to be massive, and we are going to study the information which we do have on neutrino masses. So this is kind of like so to say, a forecast of what you will see as well in these lectures. So what you see here actually is data from what is called the NewFit collaboration. They do global analysis of data, which mainly comes from neutrino oscillation experiments. So what is measured in neutrino oscillation experiments, for those who have not yet seen that, are mass square differences. We will come to this in a moment, why actually in neutrino oscillations we only measure mass square differences. But now for the moment I would like you to look at the numbers only. The mass square difference which is drawn here is of the order of 10 to minus 4, so it's 7.5 times 10 to minus 5 electron volt square. And here we have something which is an absolute value around 2.5 times 10 to minus 3 electron volt square. So these are tiny numbers. You can ask yourself, is this the only information which we actually get on neutrino masses, just these mass square differences? No. Again, cosmology is very helpful because, as I said, neutrinos have a being that light, but and weakly interacting, but at the same time being overall in the cosmos and a very large abundancy, they do have a considerable impact on what we measure in cosmology, cosmic microwave background, baryonic acoustic oscillations, also large-scale scale structure. And what you see here is the sum of the light neutrino masses. So actually for the neutrinos, so if you interpret the three species, which we have seen of light particles, as being neutrinos, then you can interpret their impact in terms of the sum of their masses. So you see this given here. And in cosmology, you would also, since cosmology is not a kind of, not dealing with a closed experiment which you do in your lab and then you can control all conditions, you do this in terms of an underlying model. And the underlying model would be, in this case, what is called the lambda CDM, so assuming cosmological constant, cold dark matter, plus neutrinos. And what you would learn here would be that you can bound the sum of the light neutrino masses, and you see actually this number is really small. It's below 1 electron volt, and if you take the standard picture, it's 0.12. This is the information coming from Planck. This is 2018, so probably some of you have seen this release. This is from 2024. This is from the Decay collaboration that did now a much better measurement. And you see that actually this goes down to 0.072 electron volts if you take the most stringent limit. So that tells you that you have now already some picture of the light neutrino mass spectrum. So that's something we also have to deal with and we have to consider. So since I'm a theorist, I would like to consider it from the theory side, in the sense of that I would like to ask myself, how can I actually produce such a mass spectrum? And also, in particular, such a mass scale, which we see, namely some particle which is very light or particles which are very light. Plus, since we are in a school on neutrinoless double beta decay, we will also think about, is there anything different between light neutrino mass with normal ordering or with inverted ordering? So what do you see here? You see here, actually, the mass is drawn in a scale which is not absolute, because as we were saying, we will see that neutrino oscillations tell us about the mass squared differences. So this splittings among here. And then the cosmology gives us a bound on the sum of all of three, which, however, doesn't tell us where is the absolute scale. So it doesn't tell us in particular where's the zero. If we take this as a mass scale, so this is like something in electron volt square, it doesn't tell us where the zero sits. So the zero might sit here, which means the lightest neutrino mass is non-zero itself. It might also sit here, which would tell us that the lightest neutrino mass actually is zero, so the lightest neutrino is massless. So some word regarding this nomenclature on why do we call this normal ordering and why is this inverted? So this is just to say normal is because you would say the one which belongs, so to say, to the first generation is the lightest, then you have the second one, and then the third one is the heaviest. This is what you is reminding you of what you see as ordering if you think about the electron is lighter than the muon, is lighter than the tau lepton. And this is true also for quarks if we think about the generation. So this is why people decided to call this is normal. So this is like you would expect it from the charged fermions, Well, this just had to have another name, so you call it inverted, because it seems to be just, in particular, you seem to have that the third one is the lightest. So it looks like flipped with respect to what you would expect from charged light. So that's now about the mass. So you could say, actually, if you are very critical, you might say like, I really don't like this information, that the very much information in particular on the scale, so the sum of the light neutrino masses actually comes from cosmology. Assume that cosmology is weird and maybe we don't have things very, very well under control because it's not an experiment which we can do in the lab and where we can control all conditions. There are actually also evidences and experiments which kind of give us control on the absolute scale of the light neutrinos, which are done in the lab. So one is searches for beta decay, and the real big experiment, big player there is the Catherine experiment. So they are measuring what is called M beta, this funny combination here, which is not under discussion in the school very much. But you see here, the mass squares are also appearing, so you can get some information also on the absolute scale of the light neutrino masses through this. As you see, this is the latest limit which came out this year, and the Catherine experiment has a forecast that they're going to reach some sensitivity, which is 0.2 electron volt, so they can also bound it. And then for this reason also bound the lightest neutrino mass, which you see here. Now this is plotting this quantity, this funny quantity here with respect to the lightest neutrino mass, the guy which sits down here. For normal ordering it's M1, and for the inverted one is M3. So you can learn something by bounding this quantity or even measuring. You can learn something about where the lightest neutrino mass sits. And now we come to the main player of the school. Obviously, neutrinos double beta decay can also tell you something about that. Here's the forecast. We will discuss all this in the course of the lectures, but just to give you like a forecast of what actually we will arrive at, is that the quantity from particle physics point of view, which is relevant for neutrinos double beta decay, is this M beta beta, or also called MEE. Also here you see the light neutrino masses are appearing. So also neutrinos double beta decay, which actually you might think is mainly a purpose for finding lepton number violation, can tell us something about the value of the lightest neutrino mass. So, but that's just like a teaser for what is coming, just to say there are different ways of getting a handle on what's the lightest neutrino mass of the light neutrinos, so on this guy. So, questions until here, where everything is clear. Another, yes, please. Yeah.
I didn't get why we need the doublet variants to be left handed and not the other part. This is a complex.
So you are questioning this one. Observation which we make. I mean, this is how the standard model is built, right? That's weak interactions are going with left-handed particles. So if you now ask, so you're asking why do we call this electron and not positron? Or I mean, you could switch everyone to be the antiparticle, so then you would write it. But that's a convention of whether you call this electron and not positron, but then you would have to revert everything in all conventions and all the conventions of the electric charge, which actually bring us to call this electron, which has a negative charge, and the positron, which has a positive one, right? But the real important point is if you divide your particles in left-handed guys and right-handed guys, then the weak interactions are only attached to these guys, only to one type. That's also why we say parity, which is the exchange between left and right, actually is maximally violated in the Standard Model. And the best example are the neutrinos, because if we now go back to this funny picture in the beginning here, you see this is the point where here's the hole, right? That's the maximal violation of of parity which you could imagine in the star model is that you have one particle which you actually need only in its left-handed incarnation. And this is the neutrino, the main player also of this school. While all the others, we know they have to have right-handed components as well, but the neutrino is the unique guy which actually can only be there in its left-handed incarnation. Does this answer the question or not? I mean, please tell me. You're asking the question, so is that okay? Good. Other questions or doubts? Yes, please. The fit to this, yeah. I mean, it's just you make. I mean, you are saying that I assume that I don't know that this is nu L, and nu tau L. I just say that there's a particle which actually has the interactions as one of these guys, and then I can just ask myself how many copies of these are there, and this influences of what is called the invisible decay width. So the number of channels which you have for the Z boson decay, right? So the mass, you mean the mass of the neutrino? I mean, you would say at that time, there were still most people believing. I mean, when they made the plot, there were a good portion of people believing that neutrinos are totally massless. So you would just switch them. I mean, the mass of the neutrinos, even nowadays, if you do your calculation of this Z boson decay, I mean, the Z boson itself, as we can see here, as a resonance, has around the mass of 91 GeV. So the light neutrinos nowadays information is they have masses in the sum of around 0.1 electron volt at maximum. So forget about these finite state masses, please. So the difference really between these curves here is really just the multiplicity of how many channels we have. Is it 2, 3, 4, or whatever? Yeah? No effect on the mass. No, no effect on the mass. Other questions? Yes, please. Mm-hmm. Mm-hmm. Yes. Yes. It's yeah. Yes. Yes. It's exact. Yes. You would. I mean, it's really corresponding to the mass eigenvalues, if you say. I mean, it's very plainly assuming you have particles which have a certain mass, and this is the same throughout the history of the universe, and so it's a constant mass, which is always the same. So it's on these two slides, it's identical. So it's M123. Yes. Another question. Yes, please. Mm-hmm. Mm-hmm. I mean, so you are asking just to understand. So assume we once know the mass, the sum of the mass, exactly, and we know the mass splitting. So then we can go to this plot if you want, right? So you can say like, assume we know the sum of the mass, we measure it, and then we can just see where, these are the two curves which we can draw for the two different hierarchies which we have. And then we can see whether there is a unique answer or not, right? Is that what you mean? Whether you can really fix then the lightest mass through knowing the sum? If you are not in this regime where you have a high mass, so then you actually, yes, you can resolve it. You see the slope here is very small, so you probably, within the error bars, you would still have some flexibility. Was that the question? Or, sorry. Which mass we can't measure? Sorry. Mm-hmm. Yes. Yeah, I mean, we have a bound until now. So we have bounds that get stronger. We also have the question whether this analysis is actually, since it's assuming that there's a standard cosmological model underlying, is this correct? So you might say any deviation in the lambda CDM model, which compared to what we assume, compared to what is realized in nature, might also have an impact on this, right? So that kind of limits this, let's say, the predictive power of these data is also hindered by the fact that, I mean, we are looking at the universe, so we have to accept our signal, what we get. We might have signal, we might have background. We have the problem of having to assume an underlying model for the evolution of the universe at all. And whatever you kind of dial in there, you might change things slightly, while affecting obviously also this, if you take this as really precision measurement, right? And it becomes a precision measurement if you say you would like to fix the lightest neutrino mass with that. But obviously you can say, if you pass on to this one here, you could say one thing you see already is that inverted mass ordering gives you usually a larger value for the sum. There are people that now start to say that this kind of starts to put under pressure the fact that neutrino masses can be inverted, because you would see this is 0.1 electron volt, here you would be 0.9, 0.09, 0.08, so you would be already here, right? But no one would claim nowadays that this measurement excludes inverted ordering, for example. But that's one thing that cosmologists take as a benchmark goal, right? Other questions? If not, I would say we switch to the theory part, in the sense that as theorists you would take it now. Sorry, actually, Giuseppe, have you took the time? When did we start? Okay, very good. Now I was not sure whether I'm going slow or I'm going fast. What I would do now with you is actually taking this data, and so the fact that neutrinos are massive, that we have some information on this delta m squares and also on the sum of the neutrino masses, as the quest of saying, okay, as a theorist, then you would have to present some Lagrangian, which includes neutrino masses. If you say the standard model strictly doesn't do this, but to have a starting point, we first look at the standard model and look how the masses of the other particles, which means of the charged fermions, are generated. So just to remind you, how are the masses of the charged fermions generated? So Yukawa couplings for charged fermions. I hope that's something you all have seen in the standard model already once in your life. And now we come back to it, and we would like to study this and we need So as you see, we introduced a new player, which is familiar to you, I guess. That's the Higgs doublet, responsible for electroweak symmetry breaking in the standard model. So if you have never seen this Lagrangian in your life, please tell me. If you have once seen it, just have a brief recap of what actually do we see here. So we see here Yukawa coupling, which generates charged lepton masses because it coupled left-handed lepton doublets with the right-handed charged leptons, here just written in the way that you have the feeling that it's the electron, muon, and tau. We do see the same also for quarks, yeah, down quarks and up quarks. So now, how actually does this proceed of getting mass? You know, this is the Higgs scalar. When this one, or its neutral component, gets a VEF, you introduce mass terms for all of the charged fermions. So let's assume the simplest thing what we can do. We try to make a copy out of one of these terms and do the same thing for neutrinos. So for this reason, we now look at what is the situation for down quarks and up quarks. Because why do we take this as inspiration? We take this as inspiration because if we look at the left-handed lepton doublets, we see in the lower components all the electron, muon, and tau sit. In the upper component, the neutrinos sit. If you remember how, for example, the left-handed quark doublet would look like, right? In the standard model, you would say for the first generation, in the upper component, you have the up quark, and the lower component, you have the down quark, just according to the name, up and down, right? So what's the difference you observe between these two types of terms? Actually, it's the same. I mean, you have a left-handed lepton doublet barred, you have the right-handed corresponding particle, right-handed down quarks, right-handed up quarks, and the unique difference lies in the fact whether you couple here phi or what is phi twiddle. Phi twiddle is actually the charge conjugate of the Higgs doublet which we have here. This is just I sigma 2, so the second Pauli matrix phi star, which gives you, if this is the 1, 2, 1 half, this gives you 1, 2 minus 1 half. Okay? So why do you do this? Why you do this difference here? Simply because we want to have a theory which respects the standard model gauge group, which means it respects in particular the U1 hypercharge. So in order to have this coupling such that we can cover the down quark and the up quark, the right-handed ones correctly, you would also have to use this one. So now take inspiration from this for writing down potentially some mass term for the neutrinos. So now if you look at the charged leptons, what appears for the charged leptons? The LL bar, obviously. Then there's some coupling matrix, the phi, so the Higgs, and the right-handed charged leptons. So what's the idea now? The basic thing, what you could do for neutrinos would be, if we want to mimic what happens in the standard model for the charged fermion masses, we would say, okay, we write down a term which is LLI bar. Then there will be some coupling matrix. And then we should use the phi twiddle instead of the phi. So what would this mean? We would have this, we said this is a 1, 2 minus 1 half. So now if you bar that, you will get a 1, 2 bar, but 2 and 2 bar are equivalent in SU2 plus 1 half. This guy here, we said this is a 1, 2 minus 1 half. So then there's something missing in here. okay? That would be like, what would we have to put in here in order as a new particle? So be fermion. Must be a right-handed fermion because all the mass terms in the standard model have this structure of being L bar R, so always combination of the left and right. So let's call this tentatively a new R. It might have an index J. And we would like to find out what are the quantum numbers which we have to put. So what would you have to put? This is your first attempt, potentially in life, to write down a mass for neutrinos, just in analogy to the masses for the charged fermions. And now you have to see what kind of new degree of freedom do we need. Okay, obviously we need a fermion. We need something which is right-handed. And what kind of quantum numbers should it have? So it should be definitely a singlet under SU3 color. Then 2 times 2 in SU2 contains a singlet, so this can be a singlet as well. Then what about the hypercharge? That's plus 1/2 minus 1/2 makes already 0. So the thing which you add also should have hypercharge 0. So that would be your simplest extension of the standard model, adding a new particle which can give you masses for neutrinos. This what is called conventionally a right-handed neutrino. Or these are right-handed neutrinos because we have an index J. So what's the peculiar thing about this? Are the properties of how it transforms. Actually, if we look at the standard model, this guy is what is called a gauge singlet. It doesn't interact at all. No color, no SU2 left quantum numbers, no hypercharge. Is really, I mean, is unique. None of the other fermions, which we know, has these properties. If it's there, then it's a very funny, unique particle because it has no gauge interactions at all. I mean, per se, if we are in the gauge basis, no gauge interactions. Then the second question you can ask, so since we were starting off with I was bothering you by saying like, let's think about why we actually know that there are 3 left-handed neutrinos. How many of the right-handed neutrinos would you need? You can have 3. I think this is in the spirit of being, let's say, nice to everyone, and everyone comes in 3 generations, so then also the right-handed neutrinos come in 3 generations. What would be the minimum would you need, however? The minimum is 2, actually. Why is the minimum 2? Can you answer this question as well? Would you know it? Yes, please. Go ahead. Yeah. Exactly. If the lightest mass, sorry, going in the wrong direction, if the scale is really that here is 0, then you're happy also with 2 right-hand neutrinos. Which already you see, in this sense, for me as a theorist, the fun part starts because I have freedom, okay? So which means like, you can consider theories where you have 2 right-hand neutrinos, which are kind of the minimalistic ones, or this is what goes under the name also of Occam's razor, so just in order to describe the data which we currently have. But you can also say like, maybe let's be nice and they are also coming in 3, or you might think about theories beyond the standard model, where you actually would unify these right-handed neutrinos with the right-handed charged leptons, so like having SU2 left doublets, you also have SU2 right doublets, then you would say they must all come in 3. But maybe you can say also, since they are so extraordinary, the gauge singlets, maybe they come in many. Maybe there are hundreds. I mean, that would be hundreds, probably would be exaggerating, but even not the number you would know, right? So just to say, like, when you start to think about neutrino masses, you usually, I mean, if you're negative, you would say you open Pandora's box, and everything can happen, so to say, more or less. If you are positive, you would say like you have a lot of opportunities to think beyond the standard model. And this is great. So for me as a theorist, at least, it's great. And I think for you as young students, it's also great because you have a lot of opportunities to look into different things. And also for experimenters, it's definitely great because you might have very different signals. And so, however, we have been, regarding one aspect, we have been very conventional until now. Because we have just copied what is here. So what happens actually by copying what is here to the neutrino nature? So now we talk about neutrino nature. Neutrino nature, then we throw in words like Dirac particle or Majorana particle. So until now, here, with writing down this mass term, neutrinos would be what is called Dirac particles. So why? Why would they be Dirac? And what's the difference to Majorana? And this is Majorana, sometimes considered to be like the holy grail for neutrinos, and where actually the real fun starts with doing neutrino physics is saying that they are really different, and maybe they are different also in their nature.
Clear to everyone why these two, right, and the neutrinos to introduce that spectrum, let's say, massive, and to have at least zero mass. No, no problem.
Okay, definitely, sure. That's, I mean, you can say it mathematically, right? Mathematically, it would mean like, look at this matrix. So this is going to be a matrix. This, if you write down then what would be the mass matrix for the neutrinos? Would be then this coupling here, Ij, so let's get Ij, and then you get a factor V over square root of 2, which comes from the VAF of this Higgs tablet, right? Now, how do you get actually from such a mass matrix the masses? Usually it tells you, take this matrix, diagonalize it, compute the eigenvalues. So what happens if you have only two right-hand neutrinos? This matrix turns out to be of this form. So you will have like three rows and two columns. So that's now the mathematics question. What's the rank of this matrix? The rank of this matrix is 2, which means you can only have two different non-zero eigenvalues. The third one is already 0 from the beginning, which means just mathematically saying if you want to have a third one that also gets a non-zero mass, you have to extend your mass matrix, at least by 1/4 the column. Is that now clear? Very good, thanks.
Then that would become a column. You only have the freedom to place 1, 0, 1 there. But you write down that you have 2 that time.
Mm-hmm. Exactly. You just get bigger. You put just more columns. Yeah? So then, good. So if there are no further questions, let's dwell into this point between Dirac and Majorana. So conventionally, all fermions which we have in the star model, they are Dirac particles. And what does it mean to be a Dirac particle? A Dirac particle means to be a Dirac, or better to say Dirac fermion, means that you have 4 independent degrees of freedom. When I say degrees of freedom, I mean you think about in spinor components. Okay? And this actually corresponds, if you now think back in what we do this usual distribution in left and right, then you would get, there are 2 from the left-handed one and there are 2 from the right-handed one. So that would mean until now, since we did nothing, we did exactly the same for the neutrinos as we did for the charged fermions. That would mean Now, until now, the neutrino would be also a Dirac particle. Then you would say you have a new left gives you 2 degrees of freedom, and the new right contains also 2 independent degrees of freedom. Then you end up with 4. So then, what else does it mean actually? Yes, let me continue there. So, what else does it mean? Now my question is more in terms of symmetry. If they are Dirac particles, now let's write down the 2 relevant terms which we have. There are more terms which then involve the particles, but if they're Dirac particles, then we would say the piece of the Lagrangian which we are now interested in looks like this. J to the J. So now we come in with a very extremely important concept which we always use, which is extremely helpful in describing many, many features of nature. We come to symmetries. Okay, so now we want to talk about symmetries which this Lagrangian has, beyond the standard model gauge group, which is SU3 color, SU2 left, U1 hypercharge. We can define a symmetry which is left invariant by these 2 pieces of the Lagrangian and also the rest of the standard model Lagrangian. So this is what is called U1L. This is lepton number. Now we come to the concept of lepton number. So what is the concept of lepton number? The concept of lepton number tells me for every lepton has lepton number plus 1, and every anti-lepton has lepton number minus 1. And all the rest of the particles, so which means what we have, quarks, Higgs, gauge bosons, have no lepton number. So these have lepton number 0. So if you now look at these pieces, so now if we constrain ourselves to the standard model, you would say, okay, this is a lepton and lepton doublet, contains leptons. But now we bar it, then it would have lepton number minus 1. This is some coupling, so this always has no quantum number. This is the Higgs, it has also no lepton number. This is the right-handed charged lepton, so the right-hand lepton. This has lepton number plus 1. So this is invariant under lepton number, okay? We do the same here. This is minus 1, 0, 0. For the right-hand neutrino, so this is a new guy. So a new guy comes to the world and to the star model. We can decide on what its lepton number is going to be. If you want to have this term invariant, we just give it the lepton number plus 1 as well. Okay, so then we have introduced, or we found, that this Lagrangian has a symmetry, which is lepton number, which is conserved, because we don't find a term which violates this number. And this is in perfect analogy to what you know from quarks, that's baryon number, right? So if you dwell more deeply into the standard model, you will find out that lepton number and also baryon number, they are both perturbatively conserved quantum numbers in the standard model as it is. Whether or not lepton number or also baryon number is conserved in any extension of the standard model, there we have to put a question mark. Okay, so but if we study the simplest extension of the standard model, which means we just throw in here right-hand neutrinos, we copy the mass temp for the neutrinos from what we learned from the charged fermions, we see that lepton number actually is conserved. There's another number other numbers which we can introduce. If we are talking about total lepton number, we can actually also talk about the individual lepton numbers. So you can also talk about individual lepton numbers. That would mean you write your total lepton number as the sum of 3 individual lepton numbers, where this is like the one which signals you that you have an electron type particle. This is the one for the muon, and this is for the tau. If you forget about neutrino masses, so no neutrino masses, then in the standard model, you will see that Le, L mu, and L tau are what is called accidental symmetries, because all terms which you can write down in the standard model are invariant under these 3 different guys separately. Obviously, if they are all invariant under these 3 guys separately, they're also invariant under the sum of all of these. So that's as far as you get without neutrino masses. We will see if you throw in neutrino masses, definitely these are violated. And phenomenologically, we already have evidence that these are violated. And the most, obvious evidence is that we do have neutrino oscillations. What does it mean? Neutrino oscillations means you would start with an electron neutrino, you produce, and in some detector you see a muon neutrino. So we have a chance to oscillate, which means these, we will learn later, these are not conserved by neutrino oscillations. But that much, we now are into the symmetries. The question is, actually, is it obligatory to have this symmetry? So the question is, so we will see these ones are already ruined by neutrino oscillations. Now the question is it obligatory to have that the total lepton number is conserved? What do you think? Is it or not? Exactly, yeah. I mean, for baryon, exactly. So exactly, you have your gauge symmetries, you write down all the terms which are allowed, and you find other symmetries. That's why you call them accidental. The point is with baryon number, if you start with baryon number, we'll say like, okay, this might be an accidental symmetry, but it seems to be really, really well preserved and respected by nature, because we have not yet seen a proton decay. I mean, the lifetime of the proton is 10 to the 33, 10 to the 34 years now, the bounds. I mean, depending on the channel of proton decay you consider. So apparently we might have symmetries which for us at the level of the standard model seem to be accidental, but are really respected by nature. So baryon number seems to be one of these candidates. So you might think baryon number maybe is gauged at a certain point or something like that. Well, now the question is, what about lepton number? So is it a must to have lepton number or not?
If you assume that the neutrino is Dirac, then it becomes the formal symmetry, right? It's no longer accidental because there's no more.
I mean, it's still accidental because you don't throw it in. So, I mean, it's only, you would only call it like a formal symmetry if you impose it yourself by hand. It's still something accidental because you just say neutrino is Dirac, and then only the terms which I can write down, they preserve also automatically lepton number. That's kind of like more consequential. The question is more like, do I have to have this as accidental symmetry as all? Could there be something which actually breaks it? And this brings us to the discussion of what if a neutrino is not a Dirac particle, but is a Majorana one? And now we come to some property which only neutrinos have. If you think about the standard model at very low energies, so what are the symmetries which are observed at very low energies. Electric symmetry is broken. But what are the residues which we really believe to be there and where we have experimental evidence that these are exact symmetries as residues from the gauge symmetry? This is QCD. So QCD seems to be really like an exact symmetry. Gluons are massless. And this seems to be electric charge. Photon is massless. We have not observed any process which breaks QCD nor breaks electric charge. So now, think about the neutrino. What are the properties of the neutrino? The left-handed neutrino. That's the one which is included in the star model. Under color and under electric charge. The neutrino has no color and it has no electric charge. So actually, then it might be, that's what is called a Majorana particle. And a Majorana particle has its definition, or as most striking characteristics. That's what the invention was of Majorana. Majorana particle, you say, is its own antiparticle. Is its own antiparticle. So there's no difference between particle and antiparticle, so it doesn't make sense to write this down. So if we write it in formula, you would see just, okay, you take the neutrino, you take its charge conjugate, it's the same. So that C here stands for charge conjugation. And obviously there's nothing which prevents me from doing that, right? It has no color, it has no electric charge, so it could well be that if I conjugate all charges, since all the charges are zero, conjugating a zero still gives me zero, so it can be its own antiparticle. And so the question is, that's what eventually Majorana was. You see, I will operate with this equation. If you want to see a generalization, in principle, you could put in a phase factor here. I won't do this for the sake of these lectures. And also afterwards, I will not put in a phase factor anywhere there. But the main standing point is that a particle is its own antiparticle. And now the question is, so in principle, so color doesn't prevent us from doing that, nor does electric charge. What kind of consequences does this equation have if we now think in terms of degrees of freedom? I was dwelling on that the Dirac particle has 4 degrees of freedom. What's the number of degrees of freedom for Majorana fermion? It's 2. Yes, that's correct, because from this equation you can derive that actually the right-handed component is the left-handed charge conjugate. So this means now you get for free some components, so to say, because they are not independent anymore. If you think now, we can do 2 things. We think first in terms of symmetries. What does it mean for lepton number then? What happens to our U1L if this equation holds? So we were saying in the beginning that leptons have lepton number plus 1, right? So now, which means antileptons have lepton number minus 1. So in this equation, we would have to write here 1 is equal to minus 1. So, which means immediately if you have a Majorana fermion, you know that this U1L is broken. definitely. That's not going to be an accidental symmetry. No way. It's not going to work. The second thing which I would like to discuss with you is actually, what does this mean for masses, for neutrino masses actually? So here we still have the Lagrangian, and we actually were saying that this one should give, this piece here should give masses to neutrinos if they are Dirac, right? So if they are Dirac, you would write, say you start with this, and then what would happen after electric symmetry breaking? With this one, you would get what I call now an M nu D, which is of this form. You cover coupling times square root of 2 V, the VEF. And where does it show up? How does the Lagrangian change? This piece here would be minus M nu J, now bar I, J. That's how this mass, so this term, when it really becomes a mass term from an interaction term, looks like if you break electric symmetry. How do you see that? You see that if you think about that the left-handed lepton doublet, you would write like nu Li, Eli, and then you would have this V twiddle that would get a VEF in this upper component, and you would just take these two vectors being multiplied, making the scalar product. Then this gives you Li bar. So the nu I bar here, you get the factor, which is the VEF. And here we have the nu I. So that's the way how a Dirac mass term would look like after electric symmetry breaking. So when we start from the Standard model. Now, take this Lagrangian and insert the Majorana condition, this one. What kind of mass term do we get then? So we would get something which we call M now. And I would write down this term here, but taking into account that I have this condition. What happens? I would get the nu L bar, I don't change, but instead of having nu Rj, I would put that actually I can express this in terms of the left-handed charge conjugate. And I would put actually here factor on 1/2 conventionally, and then I put another name for it, an MM. Okay, so I would, just doing this kind of simple replacement, which is the Majorana condition, I would get from this, what was our Dirac mass term before, I will get to this one. Yes? Clear until here? Or? Oh, the 1/2 is a convention, because what we see here now, so this is the first, maybe in your life, Majorana mass term, which you see. That's a Majorana mass term. What's the characteristics of this guy? Actually, it connects fields of the same type. Since it connects fields of the same type, it's convention to put a factor of 1/2. If you, you will see, if you ask my theory colleagues, most of them easily just write you down the Majorana mass term without a factor of 1/2, but knowing that there should be a factor of 1/2, but don't worry. But the characteristics of this guy is that this is a mass term connecting the same type of fields. So you effectively, since the right-hand component is not independent anymore, so you can live and write it down only with left-handed ones. Okay, so now we check, what about lepton number here? is violated. So by how much actually is lepton number violated? By 2 units. Exactly. Because we have here, so if we say the new L, remember it comes from the left-handed lepton doublet, has lepton number +1. So this bar gives me -1. If I charge conjugate it, it gives me also -1. So the L of this term here is -2. So which means this one is a delta L equals to 2. And now, this is fantastic. So we have seen now the first time violation of lepton number is possible. I mean, without, let's say, just breaking all the rules and all the symmetries which we know and whatever and what should be conserved. So we can do this in principle. Neutrinos can do this. Then the next question, there are 2 questions now, main routes to go. One route is a theory route. The theorists would ask, what can I do with this term at the level of the standard model? That's more or less me. The second route, which is obviously very much also justified and definitely is extremely important to pursue, is the question, how can we test that? So, the theory route we do later. Because the phenomenological route I can very briefly answer, and because we will come to this back. The phenomenological route is actually hidden in the title of this school. It's Neutrinoless double beta decay. So the most realistic chances which we ever were going to have, and the most model independent chances to verify that lepton number is violated by 2 units is the searches for Neutrinoless double beta decay. We will come to this and later. This just to answer this kind of one route, extremely important route is the experimental, the pheno route. The theory route is the one, what can I do with this term? Actually, the question is now, we are looking at this Lagrangian after electric symmetry breaking, right? Because we are writing this down for left-handed neutrinos. If we are thinking in terms of the standard model, we are obliged to write down this term, not with the left-handed neutrino alone, but we have to write it down with LL bar I, LLJ, C bar, sorry, no bar. Okay? Because we know that the left-handed neutrinos, they are contained in the left-handed lepton doublets. Question to you. Can I write down this term at the level of the standard model?
It does not work because it's not SU2 invariant when you write the terms.
I mean, so let's check. So this is having the LL bar has 1, 2 plus 1/2. The LLC has also 1, 2 plus 1/2. So regarding the SU2 left invariance, actually I could say like 2 times 2. I mean, this gives a singlet. Maybe I can survive. But one thing which definitely doesn't work is we have hypercharge here. The hypercharge of L bar and LC is the same. And the left-hand lepton doublets, they have hypercharge plus 1/2. So this definitely, if I want to write it down at the level of the standard model, breaks hypercharge. So I make a big mistake. I violate the gauge symmetry, which means you're not allowed to write down this term innocently just in your Lagrangian. So there are various ways out, and we are going to study these ways out in the following.
But in this also the coupling with the Higgs is compromised. No? Because with the master.
I mean, here
Okay,
you want to throw in some, I mean,
then the pair must without the Higgs mechanism. Okay, no, of course.
yes, so the question is actually what you're asking is like, do I actually still need a Higgs? Do I need a scalar for that? The answer would be if you write down this with left-handed lepton doublets, Yes, you do still need a scalar for that. We will see what can be options for it. If you write this down, this is another story. Whereas our beloved right neutrino, if you write it down with right neutrinos only, then obviously nothing bad happens, because if you write it down with right neutrinos, you would say this is newer bar, newer C. A right neutrino is a total gauge singlet. What for? Write it down. Be happy, and then your right neutrinos have a Majorana mass. I mean, something which might exist or not. So that's the question. If we ask the question about what we sure know, that they are left neutrinos because they're included in the standard model, are we allowed to write down a Majorana mass term plainly at the level of the standard model? Without modification? I mean, modification means standard model for me is now here all terms which I can write up to mass dimension 4, which means all renormalizable terms. The thing what you usually see in the master courses you are taking, right? Here, if you go beyond standard model, which might mean you can think about the standard model being an effective field theory, you include higher dimensional operators, then this thing becomes possible, where you have to throw in some Higgses, and we will see. That's called the Weinberg operator. Or you just extend your standard model by throwing in new scalars. Discuss this. But for the moment, I just wanted to settle the stage here by first having the experimental evidence for number of generations, the numbers for the masses, and the important difference between neutrinos being Dirac or Majorana, and the type of the mass terms which we have. And these are the two things you should keep in mind. Either you have this type of mass term, which is Dirac, or this type of mass term, which is Majorana. And yes. I mean, this is like, okay, you have seen what charge conjugation is. I mean, this is this thing where you write gamma 2, gamma 0 combination. So it's not exactly bar, because the bar would, I mean, at the level of the spinner would say you have a bar is a dagger gamma 0. So the interpretation is differently. So just to say. Regarding the quantum numbers, if you just ask what is the exactly lepton number, for example, the U1s are the same, but obviously the spinor properties, the Lorentz properties are different. Okay. Other questions? If not, I would say we 9:30. So then I get another 10 minutes. Is that correct? Giuseppe, you are agreeing? 10:15. Then I would like to do one third thing, if you have no urgent questions at the moment here. We have now introduced masses for neutrinos, to say at the very basic level, because we have Dirac masses and we have Majorana masses. I would like to come back to what we were actually starting off by saying we copy everything first, what we know from the charged fermions, we copy over to the neutrinos. There's one thing we have not actually discussed about. If you think about quark masses and quark mass terms and so forth, then there's one striking thing. What I hope you have all seen in the lectures on standard model is you say, okay, I take my Lagrangian, I write down the masses for the up quarks, I write down the masses for the down quarks. Then there comes the moment when you say, I write down originally this standard model Lagrangian in the gauge basis, but then I change the basis to the mass basis. So, which means I have to diagonalize the mass terms of the up quarks and the down quarks. You have all seen that once in your life? If not, please tell me. Why do we do this? The first thing is the question, why do we do this? We do this because when we talk about a particle, we talk about an object which has a definite mass. So we have to change the basis in order to go to the mass basis and write down everything in terms of physical particles. And however, what happens in the standard model if you change from the gauge to the mass basis? What happens? Have you heard about the CKM matrix? The Kabibo-Kobayashi-Mascara matrix? Where does this come from? Where does it sit? No, in the charge currents. Charged! The other ones. It sits in the weak charge current, so it's yes. And why do we get it?
Because we have to diagonalize the mass element up and downwards. Well, of course, only the left and the parts appear in the weak interactions, so they meet.
Apparently, we can't use the same matrix for the left-handed up quarks and the left-handed down quarks. That's what the CKM matrix tells us. That they are, so to say, what one says it's a mismatch. There's a misalignment. Let's formalize it this better. So the formulation is usually so. We do this now for leptons, because for leptons the same thing happens. So now you imagine we are after electric symmetry breaking. So we would have a mass term, a Lagrangian mass term for both the charged leptons, which would mean that we have something like Eij, Erj. This is for charged leptons. And then we will have something also for the neutrinos, and we can choose between either having the Dirac one or having the Majorana one, okay? And then here for the neutrinos, let me open, so to say, a parenthesis where you either please put the Dirac one, let's put the sign in here, so that we have plus L d nu. So this would be the Dirac case, and this one is the Majorana case. So now, in these two situations we can be. So what is the saying, like we go to the mass basis means, as you were correctly saying, diagonalizing the mass matrices, which means we have here a matrix which we call MEIJ, which is, with the conventions from above, is this Yukawa coupling matrix divided by square root of 2 times B, so the value of the Higgs. And on the other side, we have either the Dirac mass term or the Majorana mass term. So going to the mass basis means you take this as an arbitrary complex 3 by 3 matrix. How do you diagonalize it? You can diagonalize it with the help of 2 unitary transformations. And for the Dirac or the Majorana case, you either have 2 different matrices at your disposal, because we have nu L and nu R. So you do exactly the same as you would do for charged leptons. And for the Majorana case, you have only one type of matrix at your disposal, but the matrix is different, because that's something I've not mentioned yet, but you can check with the Lorentz properties that this matrix MM has to satisfy that this is a symmetric matrix. So what happens if we go to the mass basis? If we go to the mass basis, you would say we apply unitary transformations. Now let me introduce as notation the following. I call this EL is now a vector which contains the 3 left-handed charged leptons. And this I can write as a unitary matrix and a vector which I call EL M. This one is the mass basis, when I have my particles all in the mass basis. I do this for the left-handed ones. I do it also for the right-handed ones. So I also write this for ER. But I have a different matrix. I call this not UL, I call this UE, ERM. And then obviously I can do this for left-handed neutrinos, where I call this one UNU. And I can, if we have, I also do it for right-hand neutrinos. This way. If you just take this as field redefinitions, if you wish, you arrive by applying these to the terms which we have above and here on the other blackboards, you arrive at the following. You arrive at your ME, your dagger, UE. So now what does it mean being in the mass basis? This means for these mass terms to be diagonal. So it brings me to the basis in which I have ME, MU, and M tau, which means that every charged lepton has a definite mass, and I really talk about these as physical particles. Yes? So this is the usual stuff which you also do for quarks. Now for neutrinos, you have two choices. Either they are Dirac, then the story is the same. We would have this matrix sitting here. The mu, let's call it, for being sure, let's call this also MUD. You would get a U dagger, UR, and this should give you a mass matrix where you have M1, M2, M3, the masses of the 3 neutrino generations. Right? So you can do that. If it's Majorana, what happens for Majorana? For Majorana, this looks slightly different because you have this matrix here, which is symmetric. When I mean symmetric, I always refer to flavor space. So to the exchange of ij. But what can I do here? If I have this nu L bar, nu LCJ, then the transformation would look like nu dagger, nu star. So if that was a general complex 3x3 matrix, I would be in huge trouble. But if you look up mathematical theorems, it tells you if you do this with a symmetric matrix, you find the possibility of diagonalizing it with the help of the one unitary matrix. So you can also go to this mass basis. So that's the story of now you have gone to the mass basis. You can do this for both incarnations, Dirac and Majorana. Now we come to the important part. What happens to what we were saying, charged currents? So charged currents have a piece. So which charged currents? I mean weak charge currents, which interactions with the W boson, have a piece which is for the leptons of this form. Tau, alpha bar, gamma mu, alpha L, Hermitian conjugate. What happens if I apply these transformations, in particular this one and this one up here, to this Lagrangian as well? Because I have to. If I do a basis transformation, I have the choice. Either I do it for none of the terms or I do it for all of the terms. We have to do it for these mass terms in order to go to the mass basis. So we also have to do it for the Lagrangian piece here. How does this look like in the mass basis? So if we go to the mass basis, what do you get here? You get this. Now let me write this in matrix notation, just to make it easier. So we take the transformation for the left-handed neutrinos. You will get, so we get the new L now in the mass basis, bar. You get the U nu dagger. You get some gamma mu, which I just put aside here. And we have to apply for the right-handed charge, for the left-handed charge leptons, this one. So we will get this combination of matrices here, plus emission conjugate. So you would discover that you get this matrix combination in here. One from the left-handed neutrinos and one from the left-handed charge leptons. So if there's no magic happening, in the sense of magic, or particular symmetries or whatever you throw in, U nu and UL won't be the same matrices. If they are not the same matrices, this one won't be the identity matrix, which means it doesn't disappear. So what it actually is, only experiments can tell you. There's no, in the standard model, there's no theory prediction for that, nor there's a theory prediction for the CKM matrix. As you know, the elements of the CKM matrix are measured experimentally, and then we found out that the CKM matrix has the Capibot angle, which is quite large, and then the others are tiny, right? So this is something you have to measure. So, however, this is the equivalent of the CKM matrix now for the leptons. So, two things. Point number one, this one gets a special name. This is called the PMNS matrix. I'll write you out the names in a second. Actually, it's defined as UL dagger U nu. So the dagger of this. This is the Pontecorvo Maki Nakagawa Sakata matrix. So what are the properties of this matrix? So we said we always use unitary matrices here to do this basis transformation, right? This means that also these ones, so you have a combination of two unitary matrices, also this one is a unitary matrix. Okay? And this is what one usually says, this is the analog of the CK matrix. But now, for the leptons. Before finishing, I think I should finish. Yes, I should have finished already, right? Before finishing, let me please make two comments. Then I think we are good. So, comment number one is, what actually happens if neutrinos are massless? So now we were doing all this derivation, saying that there's also a mass term for neutrinos that might be Dirac or it might be Majorana, but there is one. What happens if neutrinos are massless? What happens to this matrix here?
This can get washed away by renaming of the neutrino fields.
Exactly. So if neutrinos are massless, then we have one part which you don't need to diagonalize. Then we actually only need to diagonalize this one here, right? Out of these three lines which I've written down, we only need this one. Only this one really is a must-have. Which means, on the contrary, we are not using U nu, and there's definitely also no UR. So make your choice, choose your freedom. This one, you can just freely set to UL, right? If neutrinos are massless, you don't need it effectively, because you don't need to do this diagonalization here, nor this diagonalization up there. Okay, so if neutrinos were massless, we could choose u nu to be UL. Then no PMNS, or better to say the PMNS is unphysical. Yes? That's the important point. You see that? All that's really important to see that. Mm-hmm. So if neutrinos are massless, for the leptons, you only have one mass term. Only for the charged leptons, because we know that they have mass. While we have not to bother about whether we have an M nu D or an M in the... okay, so what are the matrices which you need here? You need the UL and this UE. But there's no one that tells you which kind of form this U nu should have. Okay, take your freedom, choose it such that this also becomes invariant, so which means like your PMNS is unphysical, so there's no, I mean, that you can just rotate it away, so to say, and nothing changes. Right, so which means now we know that neutrinos are massive. We also know that this is not going to be the case, which means we know that the PMNS matrix is really contains physical observables, right? So, and yes, how do we measure these observables? We will talk about nomenclature and parameterization, etc. the next time, but how do we measure them physically? Because that we should always have in mind what's the kind of experiment which we can use in order to measure these. Neutrino oscillations, okay? And I think I should shut up now, definitely. You deserve a break. So, urgent questions we can discuss now or afterwards. I have one question to you. From the style, was it okay? Was it clear? Is that fine for you? Or is it too fast? Is it too slow? Is it... You're happy, or you're just too tired and you just want to have coffee? Or tell me. I mean, I like to have feedback from the students. No, I mean, when I get too much theorist, you just tell me, okay? You just say like, oh, no, no, no. Now you are getting too much crazy and whatever, you just tell me. So that's, I mean, can easily happen. You will see when we discuss how to generate masses from neutrinos. So what I like very much, but whenever it gets unclear, please. Okay, so also there, please stop me, because I think we have all the time. And obviously you will also have the tutorials with Joao. So you will have time also to discuss different things with Joao and ask him questions of all kinds. Okay.
If you ask Claudia to cover a fairly big amount of topics, all theories to a certain amount between phenomenology and formalism, and we allotted 8 hours to her only. I think that's the only case where a person has 8 hours for their lectures, specifically because we have a bit more time to dive into the various formal steps for all of you, not just Mr. Campbell. So slow her down if you feel that she's going too fast or something. I don't know if the audio is... the microphone? It's supposed to be working.
Yes, actually it's on. I mean, I was told that it actually is not relevant here for the room usually, but it's relevant for so they told me, I mean, if you don't use the microphone, the video will have very low audio quality. But you, I mean, now here, even you could hear me well during this, or okay, okay. So then next time I try to adjust it better, but please tell me. Okay, everyone is exhausted and tired, and then I thank you for the first lecture, for your attendance and participation.
Okay, so